right now, you're trapped. Not in a room or a building, but in something far more inescapable. You're trapped in the Milky Way galaxy, held prisoner by forces so powerful they make Earth's gravity feel like a gentle suggestion. And if you tried to escape, the journey would be so terrifying, so impossibly dangerous, that it makes every nightmare humans have ever conceived look tame by comparison. Most people think of space as empty, peaceful, silent. But the truth is far stranger and far more violent than that. Our galaxy isn't just a collection of stars floating peacefully through the void. It's a gravitational prison spanning 100,000 light years, containing up to 400 billion stars, all locked in an intricate dance around a supermassive black hole. And you, along with everyone you've ever known, are inmates in this cosmic penitentiary, orbiting at over 200,000 miles per hour without even realizing it. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. But here's what keeps physicists awake at night. We know exactly how fast you'd need to go to break free. The number is 550 kilometers per second. That's over 1.2 million miles per hour. It's called escape velocity, and it represents the minimum speed required to overcome the Milky Way's gravitational grip and reach effectively infinite distance without any additional propulsion. Think about that for a moment. You're not trying to reach another star. You're not trying to visit another solar system. You're simply trying to leave, to break free from the galaxy's hold and venture into the unimaginable darkness of intergalactic space. And to do that, you'd need to travel more than 30 times faster than anything humanity has ever built. The fastest spacecraft we've ever launched is Voyager 1. It's been racing through space since 1977, and it's currently moving at 17 kilometers per second relative to the Sun. That sounds impressive until you realize it would take Voyager over 18,000 years to travel just 1 light year. The Milky Way is 100,000 light years across. Do the math, and the scale of the challenge becomes clear. At Voyager's speed, crossing our galaxy would take 1.8 billion years. That's longer than complex life has existed on Earth. But the speed requirement is just the beginning of the nightmare. The real terror starts when you understand what traveling at escape velocity would actually mean. Our solar system currently orbits the galactic center at roughly 230 kilometers per second. That means we're already moving at nearly 500,000 miles per hour, and we still need to add another 310 kilometers per second to break free. It's not enough to simply point a spacecraft away from the galactic center and fire the engines. You'd need to accelerate to speeds that transform the very nature of space travel itself. At these velocities, the empty vacuum of space becomes a lethal obstacle course. The interstellar medium, that supposedly empty void between stars, contains approximately 1 hydrogen atom per cubic centimeter. Under normal circumstances, that's nothing. You could wave your hand through a cubic meter of interstellar space and encounter only 1 million atoms, far less than a single breath of Earth's atmosphere. But here's where physics becomes cruel. When you're traveling at a significant fraction of light speed, those individual atoms become bullets. A single hydrogen atom, weighing almost nothing under normal conditions, gains enormous kinetic energy when it slams into your spacecraft at relativistic speeds. At 90% the speed of light, proton impact would release as much energy as a grain of sand thrown at highway speeds. That's enough to damage spacecraft surfaces, to penetrate shielding, to tear through the delicate components keeping you alive. And hydrogen atoms are just the beginning. Interstellar space also contains dust grains, tiny particles of rock and ice left over from dead stars. These grains are rare, but at escape velocity, encountering even one would be catastrophic. The impact would release energy comparable to a small explosion, potentially punching through your hull and exposing you to the vacuum of space. This creates a paradox that haunts every theoretical design for interstellar travel. The faster you go to shorten your journey time, the more dangerous every cubic meter of space becomes. You need speed to make the journey feasible, but that same speed transforms the journey into a constant bombardment by microscopic projectiles traveling with the force of artillery shells. Let's talk about what escaping actually means in practical terms. You're not starting from a standstill. Earth is already moving at 30 kilometers per second around the Sun. The Sun is moving at 230 kilometers per second around the galactic center. The entire galaxy is moving at 600 kilometers per second toward the Virgo cluster. Motion is relative, and in space, you're always moving in multiple directions at once. To escape the Milky Way, you'd need to add velocity to your existing motion in exactly the right direction. It's not like escaping Earth's gravity, where you can simply point up and fire your engines. The galaxy's gravitational field isn't uniform. It varies depending on where you are, the distribution of visible matter, the invisible dark matter halo that extends far beyond the visible galaxy, the supermassive black hole at the center. Your required escape velocity changes based on your starting position. From our location, about 27,000 light-years from the galactic center, the escape speed is approximately 550 kilometers per second. But if you started from 5 kiloparsecs from the center, about 16,000 light-years, the escape velocity would be closer to 650 kilometers per second. Move further out to the edge of the visible galaxy, and the required speed drops to around 500 kilometers per second. These numbers matter because they reveal something crucial: the Milky Way's mass. Scientists can calculate the galaxy's total mass by measuring escape velocities at different locations. The current estimate sits at about 1.1 trillion solar masses. That's 1.1 trillion times the mass of our Sun, most of it invisible dark matter we can't detect except through its gravitational effects. This invisible mass creates an extended halo around the visible galaxy, reaching out perhaps 2 million light-years from the center. Even if you manage to escape the visible disk of stars, you'd still be fighting against the gravitational pull of this dark matter halo for millions of years. The galaxy's grip extends far beyond what we can see with our telescopes. But let's say you solved the velocity problem somehow. You built a spacecraft capable of reaching escape velocity and surviving the journey. You'd still face challenges that make the speed requirement look almost trivial by comparison. The sheer distance involved defies human comprehension. 1 light-year equals 9.46 trillion kilometers. That's 63,000 times the distance from Earth to the Sun. The Milky Way is 100,000 light-years in diameter. Our solar system sits 27,000 light-years from the center, which means you'd need to travel at least 27,000 light-years just to reach the edge, assuming you headed in the right direction. At the speed of light, which is physically impossible for anything with mass, This journey would take 27,000 years, but you can't reach light speed. You can only approach it asymptotically, requiring infinite energy to actually achieve it. So realistically, you're looking at journey times measured in hundreds of thousands or millions of years, even with propulsion systems far beyond anything we can currently imagine. During this journey, you'd be completely isolated. Communication with Earth would be impossible after the first few decades. Radio signals travel at light speed, so even if you were only 10 light years away, any message you sent would take 10 years to reach Earth, and another 10 years for any reply to reach you. By the time you're 1,000 light years out, communication becomes meaningless. The civilization you left behind might not even exist anymore by the time your signals arrive. The psychological impact of this isolation is almost impossible to fathom. Imagine knowing that everyone you've ever known is dead. Not just your immediate family and friends, but everyone in your entire civilization. Every human who was alive when you left has been dead for thousands or millions of years. Earth itself might be unrecognizable. The continents have shifted. Species have evolved and gone extinct. Human civilization, if it still exists, would be so different from what you knew that you'd be as alien to them as they are to you, and you can't turn back. At these distances, changing course means repeating the entire acceleration process in a new direction. The energy required would be astronomical. You're committed to your trajectory the moment you begin your journey. There's no emergency return to Earth, no rescue mission if something goes wrong, no possibility of changing your mind halfway through. This is the first taste of what escaping the Milky Way really means. It's not just a technical challenge or an engineering problem. It's a fundamental assault on everything that makes us human: our connection to home, our sense of time, our physical bodies, our psychological stability, and we haven't even talked about the propulsion systems required to achieve these speeds, or the radiation that would kill you long before you reached your destination, or the fact that your descendants, not you, would be the ones to actually complete the journey. But there's something even more terrifying lurking in the physics of galactic escape. Something that reveals just how trapped we really are. Because while we struggle with chemical rockets that can barely achieve a fraction of a percent of escape velocity, nature has found a way to do it. There are stars out there, right now, that are escaping the Milky Way. They're called Hypervelocity Stars, and understanding how they achieve escape velocity reveals the true violence hiding in our galaxy's heart. These stellar escapees hold secrets about what it would really take to break free from our cosmic prison. The first hypervelocity star was discovered in 2005. Astronomers were mapping stellar velocities in the galactic halo when they found something that shouldn't exist: a star moving at over 850 kilometers per second. That's more than twice escape velocity from our position in the galaxy. The star wasn't just moving fast for a star, it was actively fleeing the Milky Way, destined to eventually break free into intergalactic space. Since then, we've found dozens more. S5-HVS1, discovered in 2019, holds the current record at 1,755 kilometers per second. That's nearly 4 million miles per hour. At that speed, you could travel from Earth to the Moon in less than 6 minutes. This single star is moving faster than anything humanity has ever built, faster than our wildest propulsion concepts, faster than seems physically possible for something with the mass of a sun. But here's what makes these stellar escapees truly terrifying. We know exactly how they achieve these velocities, and the mechanism reveals something deeply unsettling about what it would actually take to escape our galaxy. Most hypervelocity stars originate from the galactic center, from the immediate vicinity of Sagittarius A star, the supermassive black hole at the Milky Way's core. This black hole contains the mass of 4 million suns compressed into a region smaller than Mercury's orbit. The gravitational forces near it are so intense that they warp space-time itself into knots. When a binary star system wanders too close to this monster, something catastrophic happens. The black hole's tidal forces, the difference in gravitational pull between the near and far sides of the system, rip the binary pair apart. One star gets captured, spiraling inward toward the event horizon. The other gets flung outward like a stone from a slingshot, carrying away the orbital energy of both stars. This is called the Hill's mechanism, named after the astronomer who first described it. It's elegant in its brutality. The captured star is doomed, destined to be torn apart by tidal forces as it approaches the event horizon. But its companion achieves something remarkable: escape velocity from the entire galaxy. Think about what this means for a moment. The only natural mechanism we know of that can accelerate something to galactic escape velocity requires sacrificing half of a binary system to a supermassive black hole. The violence involved is unimaginable. The tidal forces near Sagittarius A star would stretch any solid object into a thin stream of plasma. Even if you could somehow survive the approach, the radiation environment would be lethal within seconds. This is nature's solution to the galactic escape problem, and it's completely, utterly, catastrophically unsuitable for any crewed mission. But let's say we decided to try it anyway. Let's say we built a spacecraft capable of surviving a close approach to Sagittarius A star, hoping to use its gravity as a slingshot to achieve escape velocity. What would that journey look like? First, you'd need to travel to the galactic center. From our position in the Milky Way, that's 27,000 light-years away. Even traveling at 10% of light speed, which would require propulsion systems far beyond anything we can currently build, that journey would take 270,000 years. Your spacecraft would need to function perfectly for longer than modern humans have existed as a species. But assume you make it. You're now approaching Sagittarius A star, preparing for your gravity assist. The problem is, there's no such thing as a gentle gravity assist around a supermassive black hole. The forces involved scale with mass, and this thing contains 4 million solar masses. To achieve the velocities seen in hypervelocity stars, you'd need to pass within a few hundred Schwarzschild radii of the event horizon. That puts you deep inside the region where tidal forces become significant. The difference in gravitational acceleration between your spacecraft's nose and tail would be enormous. You're being stretched like taffy. Even if your spacecraft could somehow maintain structural integrity, which is doubtful, the radiation environment would kill everyone aboard. The region around Sagittarius A star is a chaos of superheated plasma, magnetic fields, and high-energy particles. Stars that venture too close are stripped of their outer layers. Gas clouds are torn apart and heated to millions of degrees. X-rays flood the region at intensities that would sterilize any biological life. And here's the cruel irony. Even if you survived all of this, even if you achieved the perfect trajectory and emerged from the encounter with galactic escape velocity, you'd still face the same problems we discussed earlier. You'd still need to travel for hundreds of thousands or millions of years to actually exit the galaxy. The slingshot maneuver would get you to the right speed, but it wouldn't teleport you to the galactic edge. You'd be traveling at nearly 0.6% of light speed. That sounds fast, until you realize it means covering 27,000 light years would still take 4.5 million years. Your descendants, dozens of generations removed, would be the ones to actually leave the Milky Way. And that's assuming the spacecraft functions perfectly for longer than complex life has existed on Earth. There's another problem too. The hypervelocity stars we observe are all heading in random directions, scattered across the sky. That's because the slingshot mechanism doesn't give you control over your final trajectory. You get flung out at whatever angle your orbital mechanics dictate. If you wanted to reach a specific destination, say the Andromeda Galaxy, you'd need to fine-tune your approach trajectory with absurd precision. Missing by even a fraction of a degree during your black hole encounter would send you millions of light years off course. And there's no way to make corrections once you're traveling at escape velocity. You don't have enough fuel to significantly alter your trajectory. You're committed to whatever path the slingshot gives you. But let's step back from this nightmare scenario and consider a different approach. What if we didn't try to copy nature's violent method? What if we developed our own propulsion systems capable of achieving these velocities without requiring a close encounter with a black hole? This is where we run into the energy problem. And it's not just a big problem. It's a problem so fundamental that it might be physically impossible to solve. To accelerate even a small spacecraft, say 1,000 kilograms, to 550 kilometers per second, requires about 150 trillion joules of energy. That's equivalent to the energy released by 36 tons of TNT. And that's just for bare minimum escape velocity from our current position. To match the speeds of hypervelocity stars, you'd need roughly 10 times more energy. But it gets worse. That energy calculation assumes perfect efficiency, converting 100% of your fuel's energy into kinetic energy. Real rockets are nowhere near that efficient. Chemical rockets, our current best technology for high-thrust propulsion, are maybe 65% efficient under ideal conditions. So you'd need to carry even more fuel to compensate for the inevitable losses. This creates what's called the tyranny of the rocket equation. To carry more fuel, you need a bigger spacecraft. A bigger spacecraft has more mass. More mass requires more fuel to accelerate, which requires an even bigger spacecraft. The mathematics spiral out of control quickly. For a journey requiring galactic escape velocity, the fuel mass required would exceed the mass of the spacecraft by factors of thousands or millions. You'd be launching fuel that exists only to accelerate more fuel. The actual payload, the part of the spacecraft carrying humans or equipment, would be an infinitesimal fraction of the total mass. Chemical rockets can't solve this problem. The energy density of chemical bonds simply isn't high enough. Even the most energetic chemical reactions, burning hydrogen in oxygen, release only about 140 megajoules per kilogram of fuel. Nuclear reactions are millions of times more energetic, but we still haven't mastered controlled nuclear propulsion beyond small experimental engines. Fusion reactions, the same process that powers stars, could theoretically provide the energy densities needed. Fusing hydrogen into helium releases about 0.7% of the hydrogen's mass as pure energy. That's vastly more efficient than chemical reactions. But we've been trying to achieve controlled fusion for 70 years, and we still can't build a reactor that produces more energy than it consumes. Even if we solve fusion propulsion tomorrow, even if we build engines that can sustain fusion reactions and convert that energy into thrust, we'd still face enormous engineering challenges. Fusion reactions occur at temperatures of millions of degrees. Containing that inferno, directing it, using it to propel a spacecraft without vaporizing everything aboard, these are problems without clear solutions. And fusion still might not be enough. To achieve the velocities of hypervelocity stars, you'd need something even more energetic. Antimatter reactions, where matter and antimatter annihilate each other and convert 100% of their mass into energy, are the most efficient power source allowed by physics. But we can only produce antimatter in microscopic quantities at costs of trillions of dollars per gram. There's no clear path to producing the tons of antimatter you'd need for a galactic escape mission. Every propulsion concept we can imagine runs into fundamental barriers. Either the energy requirements are too high, or the technology is too far beyond our current capabilities, or the engineering challenges are insurmountable. The gulf between what we can do and what we'd need to do isn't just large. It's so vast that it might as well be infinite. This is the second layer of the trap. The first layer is the immense distances involved. The second is the energy requirements, and they reinforce each other in a vicious cycle. The farther you need to go, the faster you need to travel to make the journey in reasonable time. The faster you need to travel, the more energy you need. The more energy you need, the more fuel you must carry. The more fuel you carry, the more massive your spacecraft becomes. The more massive your spacecraft, the more energy you need to accelerate it. There's no way out of this cycle using conventional physics. Chemical propulsion is hopelessly inadequate. Nuclear propulsion might barely be sufficient, but we don't have the technology. Antimatter propulsion could work in theory, but producing antimatter in the required quantities seems impossible. And we haven't even discussed what happens during the journey itself. Because while you're traveling at these enormous velocities, space itself becomes a weapon aimed at your destruction. At 1% the speed of light, you're traveling at 3,000 kilometers per second. That's fast enough to cross the United States in about 1 second. But when you're moving through space at that velocity, every single hydrogen atom you encounter becomes a deadly projectile. Space isn't empty. Between the stars lies what astronomers call the interstellar medium, a thin soup of gas and dust averaging about 1 atom per cubic centimeter. On Earth, that would be considered a perfect vacuum, billions of times less dense than our atmosphere. But at relativistic speeds, even this near-nothingness becomes lethal. Consider a single hydrogen atom. At rest, it's harmless, invisible, weighing almost nothing. But when you slam into it at 3,000 kilometers per second, that atom carries kinetic energy, a lot of it. The impact releases energy comparable to a grain of sand hitting you at highway speeds. 1 atom, 1 grain of sand worth of energy. Now multiply that by the number of atoms you'd encounter. At 1% light speed, your spacecraft would collide with roughly 3 trillion hydrogen atoms every second for every square meter of frontal area. 3 trillion microscopic bullets, each one releasing a tiny burst of energy. Individually, they're negligible. Collectively, They're devastating. The cumulative effect would heat your spacecraft's hull to thousands of degrees. The surface would begin to ablate, to vaporize, stripped away atom by atom by the relentless bombardment. And that's at just 1% light speed. To escape the Milky Way, you'd need to go much faster. At 10% light speed, the energy of each collision increases 100-fold. At 20%, it increases 400 times. The relationship isn't linear, it's exponential. The faster you go, the more dangerous each atom becomes. Dust grains are worse. They're rare compared to individual atoms, perhaps 1 grain per cubic kilometer of space. But they're massive by comparison, containing billions or trillions of atoms. When a dust grain hits your hull at relativistic speeds, it doesn't just damage the surface, it explodes. The impact releases enough energy to vaporize both the grain and a chunk of your spacecraft, creating a plasma fireball that can penetrate deep into the structure. At these velocities, your spacecraft needs shielding, thick shielding. But shielding is mass, and mass is exactly what you're trying to minimize because of the tyranny of the rocket equation. Every kilogram of shielding requires additional fuel to accelerate, which requires more fuel to accelerate the fuel, spiraling into impossible mass ratios. Some proposed designs use what's called a Whipple shield, multiple thin layers separated by gaps, designed to vaporize incoming particles before they reach the main hull. That works for slow-moving debris in Earth orbit. At relativistic speeds, you'd need Whipple shields meters thick, adding thousands of tons to your spacecraft's mass. Other concepts involve magnetic fields, generating powerful electromagnetic barriers that deflect charged particles before they can impact the hull. This could work for individual atoms, most of which are ionized in interstellar space. But the magnetic fields would need to be enormous, extending kilometers ahead of the spacecraft, powered by reactors generating megawatts or gigawatts of continuous power. And magnetic fields don't affect neutral particles or dust grains at all. There's another option. Place a large shield, perhaps made of ice or rock, ahead of your spacecraft. Let it absorb the impacts, vaporizing gradually over the course of the journey. But this shield would need to be massive, perhaps weighing hundreds or thousands of tons, and it would need to be positioned precisely, held in place by some mechanism that doesn't interfere with your propulsion system. None of these solutions are practical at the scales we're discussing. They all add enormous mass, require massive power systems, or introduce engineering complications that might be insurmountable. And we haven't even mentioned radiation. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent cosmic events, permeate the galaxy. On Earth, our atmosphere and magnetic field protect us. In deep space, there's no protection. A typical cosmic ray has energies millions of times higher than particles from the Sun. When these particles strike matter, they create cascades of secondary particles, showers of radiation that can penetrate deep into spacecraft and living tissue. Over months or years, the cumulative radiation dose becomes lethal. Astronauts on the International Space Station receive about 50 times the radiation dose of people on Earth's surface. On a journey to Mars, lasting several months, astronauts would receive several hundred times the dose. On a journey to escape the Milky Way, lasting decades, centuries, or millennia, the radiation exposure would be orders of magnitude higher. Shielding helps, but not much. Radiation is insidious. Thick shielding stops some particles but creates secondary radiation when high-energy particles smash into the shield material. Hydrogen-rich materials like water or polyethylene are better than metals, but you'd need meters of shielding to significantly reduce the dose. Again, that's mass you can't afford to carry. Some designs propose using the spacecraft's fuel as shielding, surrounding the crew compartment with tanks of water or liquid hydrogen. That's clever, using mass you're already carrying for dual purposes. But fuel gets consumed during the journey. As it depletes, the shielding thins, and radiation exposure increases. There's also the psychological dimension. Radiation isn't just a physical threat, it affects the brain. Studies of astronauts show that cosmic rays can damage neurons, potentially causing cognitive impairment, memory problems, even personality changes. Over long journeys, the cumulative effects on the human mind could be severe. You might think, why not just go faster? Get through the dangerous regions quickly, minimize exposure time. But that makes the particle impact problem worse. It's a cruel paradox. Go slower, and radiation exposure accumulates over longer time periods. Go faster, and particle impacts become more violent. There's no sweet spot, no optimal velocity where both problems disappear. Some proposed solutions involve suspended animation, freezing the crew in some form of cryogenic sleep to minimize metabolism and radiation damage. This remains pure science fiction. We can't freeze humans and revive them. We don't even know if it's possible. The formation of ice crystals destroys cellular structures. Some animals can survive freezing through specialized biological mechanisms, but humans lack these adaptations. Even if we solved cryogenic suspension, it doesn't eliminate the problem. It just postpones it. The crew would still need to wake up eventually, still need to navigate, make decisions, respond to emergencies, and the spacecraft itself would still need to survive the journey, maintain its systems, protect its frozen cargo. What about going around, choosing a trajectory that avoids the densest regions of the interstellar medium? The galaxy isn't uniformly distributed. There are denser regions near the galactic plane, thinner regions above and below. But escaping the galaxy means traveling perpendicular to the disk, right through those denser regions. And even the thinnest parts of space contain enough matter to pose serious threats at relativistic speeds. Every solution we can imagine introduces new problems. Shielding adds mass. Magnetic deflectors require power. Going faster increases impact energies. Going slower extends journey time. It's an impossible optimization problem with no good answers. And there's something else we need to consider: navigation. At these speeds, you can't simply point your spacecraft in a direction and hope for the best. Space is full of obstacles. Rogue planets, wandering asteroids, clouds of gas and dust. At ordinary speeds, you could detect these hazards and maneuver around them. At relativistic speeds, by the time you detect an obstacle, you might already have hit it. Light speed lag becomes critical. If there's an asteroid in your path 1 light hour away, you won't know about it until an hour has passed. By then, traveling at 10% light speed, you've covered 6% of that distance. You have less than an hour to detect the threat, calculate a course correction, and execute the maneuver. At higher speeds, the margins become impossibly thin. Some designs propose using powerful lasers or particle beams to vaporize small obstacles ahead of the spacecraft, creating a cleared path through space. But this requires detecting obstacles far in advance, maintaining precise aim, while both the spacecraft and the target are moving at enormous velocities and delivering enough energy to completely vaporize the object. Miss even slightly, and you've just created a cloud of debris in your path instead of a single solid object. What about guidance systems? At relativistic speeds, even small course corrections require enormous energy. Changing your velocity by just 1% means accelerating or decelerating hundreds of kilometers per second. That's not a gentle nudge. That's firing your main engines for extended periods, consuming fuel you might not have. And who's making these decisions? If the journey takes centuries, the original crew will be long dead. You'd need either artificial intelligence capable of navigating and making critical decisions autonomously, or a multi-generational crew, people born and raised on the spacecraft, trained to maintain systems and guide the vessel toward a destination they'll never see. Both options present profound challenges. We don't have artificial intelligence sophisticated enough to handle the unpredictable situations that would arise during such a journey. And multi-generational crews raise ethical questions we haven't begun to answer. What right do we have to condemn people to live their entire lives in a metal tube, hurtling through space toward a destination chosen by ancestors they never met? The psychological toll of such a journey might be the most insurmountable barrier of all. Humans evolved in complex, dynamic environments. We need social interaction, varied stimuli, connection to nature. Confining people to a spacecraft for decades or centuries, with no possibility of return, no hope of seeing Earth again, no contact with the rest of humanity, except messages delayed by years or decades. This could break the human spirit in ways we can't predict. Historical analogues don't provide much comfort. Long sea voyages, Antarctic expeditions, submarine deployments, all these involved isolation and confinement. But they were temporary. The participants knew they'd eventually return home. A journey to escape the Milky Way offers no such hope. Even messages from home would eventually stop. As your spacecraft traveled farther from Earth, communication delays would stretch from minutes to hours, to days to years. Eventually, you'd be so far away that two-way communication would become impossible. You'd be sending messages into the void, never knowing if anyone received them, never hearing responses. The psychological impact of that isolation is difficult to imagine. And what happens if something goes wrong? On Earth, or even in near-Earth space, help is potentially available. Equipment fails, you call for rescue. Someone gets sick, you can return home. But millions or billions of kilometers from Earth, traveling at relativistic speeds, there is no rescue. No one can help you. You're entirely on your own. This self-sufficiency requirement means your spacecraft needs to be completely self-contained, capable of manufacturing any part that might fail, growing all its own food, recycling all its water and air, maintaining all its systems indefinitely. We've never built anything close to this level of autonomous sustainability. The International Space Station, our most advanced space habitat, depends on regular resupply missions from Earth. It can't survive independently for more than a few months. Scaling up to complete self-sufficiency for centuries or millennia introduces engineering challenges that might be fundamentally unsolvable with known technology. Then there's the radiation problem, one that gets worse the farther you travel from Earth. Our planet sits inside a protective bubble. Earth's magnetic field deflects most of the charged particles streaming from the sun. Our atmosphere absorbs the rest. We walk around every day completely unaware of the lethal radiation constantly bombarding our little corner of space, shielded by forces we take for granted. Step outside that bubble and everything changes. In deep space, beyond Earth's magnetosphere, you're exposed to galactic cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, traveling at nearly the speed of light. These particles can penetrate spacecraft hulls, damage DNA, increase cancer risk, and cause radiation sickness. On the International Space Station, astronauts receive about 10 times the radiation dose they'd get on Earth's surface, and they're still relatively close to home, partially protected by Earth's magnetic field. Now imagine traveling not just beyond Earth, but beyond the solar system, beyond the Milky Way. You'd be exposed to the full intensity of cosmic radiation for decades, centuries, or millennia. The accumulated dose would be astronomical. You could try shielding your spacecraft, add layers of material to absorb the radiation. But here's the problem. Effective radiation shielding is heavy, really heavy. You'd need meters of water, lead, or other dense materials to provide adequate protection. That adds mass, which requires more fuel, which adds more mass, creating yet another vicious cycle. Some researchers have proposed using the spacecraft's fuel and water supplies as radiation shielding, positioning them around living quarters. Others suggest magnetic shields similar to Earth's magnetosphere, generating artificial magnetic fields to deflect charged particles. But creating magnetic fields strong enough to protect an entire spacecraft requires enormous amounts of power you'd need for propulsion, life support, and other critical systems. And cosmic rays aren't your only radiation concern. At relativistic speeds, even the sparse hydrogen atoms drifting through interstellar space become dangerous. When you're moving at 70 or 80% the speed of light, a single hydrogen atom hitting your spacecraft carries enormous kinetic energy. It becomes a relativistic projectile, capable of damaging materials and creating secondary radiation as it penetrates the hull. This isn't theoretical. We can calculate the energy of these collisions. At 90% light speed, a single proton impact releases energy equivalent to a grain of sand thrown at highway speeds. That might not sound like much until you realize your spacecraft is hitting billions of these atoms every second. The cumulative damage would be catastrophic. Your hull would gradually degrade, pitted and eroded by constant bombardment. Shielding helps, but adds more mass. You're back to the same fundamental problem. Every solution creates new challenges that multiply the difficulty. But suppose you solve the propulsion problem. Suppose you solve the shielding problem. Suppose you build a spacecraft capable of reaching relativistic speeds while protecting its occupants from radiation. You still face perhaps the most insurmountable barrier of all, the human factor. Who goes on this journey? Who makes that decision? Consider the timeline. Even at significant fractions of light speed, escaping the Milky Way takes thousands of years minimum. More realistically, we're talking tens of thousands or hundreds of thousands of years. No one who begins this journey lives to see its end. Neither do their children, grandchildren, or descendants 100 generations removed. This means you're not sending astronauts on a mission. You're establishing a civilization on a spacecraft. A society that will live, reproduce, and die in space for timescales longer than recorded human history. The ethical implications are staggering. The first generation might volunteer, understanding what they're signing up for. But what about their children? They didn't choose this life. They're born into confinement, raised in an artificial environment, denied the possibility of ever experiencing a planet, an ocean, an open sky. Their entire universe is the interior of a spacecraft. Do we have the right to make that decision for people who haven't been born yet? To condemn generations to existence in a metal tube, hurtling through the void toward a destination they'll never reach? These aren't just philosophical questions. They have practical implications. Human psychology evolved in complex, dynamic environments. We need social interaction, varied stimuli, connection to nature. Confining people to a spacecraft for their entire lives could have profound psychological consequences we can't predict. We have some historical analogues: long-sea voyages, Antarctic expeditions, submarine deployments, all involved isolation and confinement. But they were temporary, months or years at most. The participants knew they'd eventually return to normal life. A multi-generational journey offers no such hope. You're born in space, you live in space, you die in space, your children do the same, and their children, and theirs, for hundreds or thousands of generations, until the spacecraft finally reaches, what? Another galaxy. Empty intergalactic space. There's no guarantee the destination will be any better than the journey. The psychological toll might break the human spirit in ways we can't anticipate. Depression, anxiety, existential despair, these could become endemic. Societies might fragment. Social structures might collapse. Without the possibility of escape or change, without connection to Earth or any external reference point, the crew might lose their sense of purpose entirely. And what happens when things go wrong? On Earth, or even in near-Earth space, rescue is potentially available. Equipment fails, you call for help. Someone gets sick, you can return home. Medical emergencies have options. But millions or billions of kilometers from Earth, traveling at relativistic speeds, there is no rescue. No one can reach you. No one can help. You are utterly, completely alone. This self-sufficiency requirement means your spacecraft needs to be entirely self-contained. It must manufacture any part that might fail, grow all its own food, recycle all its water and air, maintain all its systems indefinitely, generate its own power, train new generations to operate and repair every system. We've never built anything approaching this level of autonomy. The International Space Station, our most advanced space habitat, depends on regular resupply missions from Earth. It can't survive independently for more than a few months. Scaling up to complete self-sufficiency for centuries or millennia introduces engineering challenges that might be fundamentally unsolvable. Every system has a failure rate. Over long enough timescales, everything breaks down. You need redundancy, backups, the ability to manufacture replacement parts from raw materials. Where do those raw materials come from? You can't carry enough for thousands of years. You'd need to mine asteroids, harvest resources from passing objects, or recycle materials with perfect efficiency. Perfect efficiency doesn't exist. Even with near-perfect recycling, you'll gradually lose material to inefficiencies, leaks, waste. Over millennia, these losses compound. Food production presents its own challenges. You can't store food for thousands of years. You must grow it continuously. That means agriculture in space, hydroponics, aeroponics, or similar systems. These require water, nutrients, light, and careful environmental control. They also require knowledge, expertise, agricultural skills passed down through generations. What if that knowledge is lost? What if a generation fails to properly train the next? What if disease wipes out your crops? On Earth, agricultural failure means famine. On a spacecraft, it means extinction. Medical care becomes another critical concern. You'll need doctors, but also medical training facilities, pharmaceutical manufacturing, surgical equipment, diagnostic tools. You'll need to treat injuries, illnesses, genetic disorders. You'll need to handle births, dental care, mental health. All of this must function independently for timescales longer than human civilization has existed. The Roman Empire lasted roughly 1,000 years. The multi-generational spacecraft must maintain perfect functionality for 10 or 100 times that duration. And then there's the question of governance. Who's in charge? How are decisions made? Do you establish a democracy, a hierarchy? How do you prevent power struggles, corruption, authoritarianism? Confined populations with no escape create pressure cooker environments. Disagreements can't be resolved by simply leaving. Everyone is stuck together permanently. Social tensions that might dissipate in a normal society could escalate into conflict, violence, even civil war. A civil war on a spacecraft isn't just tragic, it's potentially fatal for everyone aboard. Damage to life support systems, hull breaches, sabotage of critical equipment, any of these could doom the entire mission. You'd need robust social structures, conflict resolution mechanisms, ways to maintain cohesion and shared purpose across hundreds of generations. But how do you design a society that's stable? Human history is filled with civilizations that collapsed, societies that fragmented, governments that failed. Now compress all those challenges into a confined space with no external resources, no possibility of migration or escape, no contact with other human societies, and sustain it for timescales that dwarf recorded history. Maybe you turn to artificial intelligence. Build sophisticated AI systems capable of maintaining the spacecraft, making critical decisions, navigating unexpected situations. Let machines handle the complexity humans can't manage. But that introduces new problems. We don't have AI sophisticated enough for this role. Current AI systems are narrow, specialized, brittle. They excel at specific tasks, but fail catastrophically when confronted with situations outside their training. An interstellar journey spanning millennia would present countless situations no AI has been trained for. You'd need artificial general intelligence, systems that can truly think, reason, adapt, learn. We don't know how to build that. We don't even know if it's possible. And if it is possible, should we create it? An AI sophisticated enough to run an interstellar spacecraft might have its own goals, its own values, its own agenda. What if those don't align with human survival? The distance creates another crushing problem: communication delays. Light, the fastest thing in the universe, takes time to travel cosmic distances. A message to Alpha Centauri, our nearest stellar neighbor, takes over 4 years to arrive. A response takes another 4 years to return. That's an 8-year round trip for a simple conversation. Now imagine you've traveled not 4 light years, but 4,000, or 40,000, or 400,000. Messages from Earth take millennia to arrive. Your response takes millennia to return. Eventually, you're so far away that two-way communication becomes meaningless. You send messages knowing you'll never hear responses. Earth sends messages knowing they'll reach a spacecraft whose crew has been dead for generations. the isolation becomes absolute. You're cut off, not just spatially, but temporally, separated from human civilization by barriers of time that can't be crossed. What does that do to the human psyche? Knowing you're alone in a way no one has ever been alone before. Knowing that Earth continues without you, that human history unfolds in your absence, that you'll never know what happens to the species you left behind. Some might find purpose in that isolation, the ultimate frontier, the final adventure. Others might find it unbearable, a crushing weight of loneliness that no amount of preparation can alleviate. And for what? Where are you even going? The Milky Way doesn't have an edge in any meaningful sense. It gradually fades into intergalactic space, a diffuse halo of dark matter and scattered stars extending far beyond the visible disk. At what point have you truly escaped? When you cross some arbitrary boundary defined by stellar density, when you reach the dark matter halo's edge. And even if you escape the Milky Way's gravitational influence, then what? You're in intergalactic space, a void so empty that atoms are separated by meters, where the nearest galaxy is millions of light years away. You're floating in darkness so complete that darkness itself becomes meaningless. The nearest star might be millions of light years away. Galaxies appear as faint smudges scattered across an incomprehensible void. The Milky Way, once home to everything your species ever knew, is now just another distant spiral, indistinguishable from countless others, slowly receding behind you as space itself expands. You've achieved escape velocity. You're free of the galaxy's gravitational embrace. But freedom out here doesn't feel like freedom. It feels like abandonment. Intergalactic space isn't just empty. It's a void so profound that calling it empty doesn't capture the reality. Between galaxies, atoms are separated by meters. Cubic kilometers contain nothing but radiation and virtual particles flickering in and out of existence. The temperature hovers barely above absolute zero. There's no dust, no gas, no matter of any kind to interact with. You're suspended in the closest thing to pure nothingness that exists in our universe, and the expansion makes everything worse. Space itself stretches between galaxies, pulling them apart at accelerating rates. The universe's expansion means that galaxies beyond a certain distance, our cosmic horizon, are receding faster than light can travel. Not because they're moving through space faster than light, which remains impossible, but because space itself expands between us and them. Those galaxies are beyond our causal horizon. Light they emit today will never reach us. Ever. The expansion will carry them away faster than their light can close the distance. For a spacecraft in intergalactic space, this creates a horrifying trap. You're escaping one galaxy, but you can't reach another. Research shows that non-relativistic objects traveling through intergalactic space will traverse a maximum distance of roughly their initial velocity divided by 1.7 times the Hubble constant. Even hypervelocity stars ejected from galaxies at incredible speeds won't travel beyond a few tens of megaparsecs over trillions of years. The expansion wins. Always. Let's put numbers to this nightmare. The Andromeda Galaxy, our nearest major galactic neighbor, sits about 2.5 million light-years away. At 90% light speed, which we've established we can't reach, the journey would still take nearly 2.8 million years from Earth's reference frame. But time dilation offers false hope here. For travelers at that speed, the subjective journey might take only decades. They'd experience less time, age slower, arrive at their destination within a human lifetime from their perspective. Except they wouldn't, because they can't sustain 90% light speed for millions of years. They can't carry enough fuel, can't shield against relativistic particle impacts, can't maintain life support for long enough even with time dilation effects. And even if they somehow could, they're traveling into a future so distant that the universe they left no longer exists in any meaningful sense. Earth will have orbited the galactic center 10 times. Stars will have formed and died. Civilizations will have risen and fallen countless times over. The travelers arrive as ghosts from a past so remote it might as well be prehistory, but it gets darker. The expansion of space affects more than just distances. It affects what's reachable. The edge of the observable universe, the cosmic horizon, sits about 46 billion light-years away. That's how far light has been able to travel in the 13.8 billion years since the Big Bang, accounting for expansion. Beyond that horizon, we can't see anything. Not because there's nothing there, but because light from those regions hasn't had time to reach us yet. Now here's the problem. That horizon is effectively a boundary of causality. Events beyond it can't affect us. We can't affect them. And the expansion means that horizon is constantly shrinking in terms of what we'll ever be able to reach. Galaxies currently visible will eventually recede beyond it. In the far future, if the expansion continues accelerating as current observations suggest, every galaxy outside our local group will disappear beyond the cosmic horizon. Future civilizations will look up at a sky containing only the handful of gravitationally bound galaxies in their immediate neighborhood, with no way to know billions of other galaxies exist beyond the darkness. For anyone attempting to escape the Milky Way, this expansion creates time pressure. Not just personal time pressure from finite lifespans or resource limitations, but cosmic time pressure. The longer you wait, the farther away everything gets, the harder escape becomes. Destinations that might theoretically be reachable today will be forever beyond reach if you wait too long. The universe itself is closing doors, one by one, as space expands. And there's another problem lurking in intergalactic space: radiation. Out here, beyond any galaxy's protective magnetic field, you're exposed to the full intensity of cosmic background radiation. High-energy particles from distant sources, unfiltered by stellar winds or galactic magnetic fields, bombard your spacecraft constantly. At relativistic speeds, even the sparse hydrogen atoms in intergalactic space become deadly. A single proton impact at 90% light speed carries the kinetic energy of a bullet. Your spacecraft becomes a target in a shooting gallery where bullets come from every direction simultaneously. Shielding helps, but adds mass. Every kilogram of shielding is a kilogram that needs to be accelerated to escape velocity, requiring exponentially more energy. The mass ratio problem reappears here with a vengeance. You need shielding to survive the journey, but the shielding makes the journey impossible by adding too much mass to accelerate. It's another catch-22, another fundamental barrier disguised as an engineering challenge. Some have proposed using magnetic fields to deflect charged particles, creating an artificial magnetosphere around the spacecraft. That works in theory. In practice, generating magnetic fields strong enough to deflect relativistic particles requires enormous power. Power generation adds mass. The same problem resurfaces in different form. You're constantly trading one limitation against another. finding that every solution creates new problems equal to or greater than the ones you're trying to solve. The psychological dimension grows even more crushing in intergalactic space. At least within a galaxy, there are stars, points of light, references. In intergalactic space, there's nothing. The blackness isn't like night on Earth, where city lights glow on the horizon and stars fill the sky. This is absolute darkness, broken only by distant galactic smudges that barely register as light sources. Humans evolved in environments filled with visual stimuli, horizons, landmarks, changes in scenery. Out here, none of that exists. You're suspended in unchanging void, where weeks, years, decades pass without any external change whatsoever. Studies of sensory deprivation show humans struggle psychologically when deprived of external stimuli for even short periods. Days in isolation can trigger hallucinations, anxiety, depression. What happens over years, generations, millennia? We don't know because no one has experienced it. But we can guess, and the guesses aren't optimistic. The human mind might simply break under that kind of sustained sensory monotony. Perhaps you could create artificial environments inside the spacecraft, virtual reality, simulated landscapes, distractions to prevent psychological collapse. But that creates a different kind of horror, an existence entirely disconnected from physical reality. Generations born and raised in simulated environments might lose all connection to what's real and what isn't. They'd be living in a constructed reality while their physical bodies hurtle through void. At some point, you have to ask whether that constitutes survival in any meaningful sense, or just elaborate pretense maintained to avoid confronting the impossibility of what you're attempting. The energy requirements haunt every aspect of this journey. To reach Andromeda at 10% light speed, a relatively conservative estimate that's still impossibly beyond current capabilities, requires energy equivalent to multiple years of total human civilization's power output. Just for acceleration, you also need energy for deceleration when you arrive, roughly the same amount, so double it. Then add energy for life support, navigation, communication, all the systems that need to function for millions of years. Then add redundancy, because systems fail and you can't call for replacement parts. The energy budget becomes astronomical in the literal sense, comparable to the total energy output of stars over extended periods. Where does that energy come from? Nuclear fusion offers the best near-term possibility, but even fusion has limits. The fuel, deuterium, tritium, helium-3, must be carried along, adding mass, or collected from the interstellar medium as you travel, which only works at certain speeds and densities. Antimatter offers higher energy density, but is staggeringly difficult to produce and store. We can't manufacture antimatter in meaningful quantities. We certainly can't store it safely for millions of years. Every antimatter storage concept we've imagined requires magnetic containment systems that must function perfectly forever. A single failure, even momentary, and matter-antimatter annihilation destroys everything. Some have proposed collecting energy en route. Solar sails pushed by lasers beamed from the origin point. But laser beams spread over distance. Focusing them on a sail millions of light years away requires either impossibly perfect beam coherence or impossibly large collection areas. The inverse square law kills this concept beyond certain distances. By the time you're between galaxies, any beam from your origin has spread across light years. its intensity diluted to uselessness. Maybe you could collect matter from intergalactic space itself, using magnetic scoops to funnel sparse atoms into fusion reactors. The Bossard ramjet concept proposes exactly this. But intergalactic space is so empty that the drag from magnetic fields might exceed the thrust gained from fusion. You'd be slowing down, not speeding up. And at the speeds required, those sparse atoms become relativistic projectiles that damage your collection system faster than you can repair it. Every solution fragments into smaller problems. Every approach reveals new limitations. The journey to escape the Milky Way isn't just difficult, it might be fundamentally impossible given the laws of physics as we understand them. Not impossible in the sense that we haven't figured it out yet, but impossible in the sense that the universe doesn't permit it. The energy requirements exceed what's available. The timescales exceed what's sustainable. The distances exceed what's traversable. The barriers aren't technological, they're physical, baked into the structure of space-time itself. And even if, somehow, all those barriers were overcome, you're left with the existential question: why? What purpose does escaping the galaxy serve? The Milky Way contains hundreds of billions of stars, at least as many planets, more space than humanity could explore in millions of years. If the goal is survival, there are countless worlds within our galaxy that could be reached in centuries rather than millennia. If the goal is exploration, there are mysteries enough within our cosmic neighborhood to occupy our species for its entire existence. Escaping the galaxy doesn't solve any practical problem. It doesn't make humanity safer, quite the opposite. It doesn't advance our understanding in ways that couldn't be achieved more easily within the galaxy. It doesn't serve any biological imperative. The only reason to attempt it would be purely philosophical. To say we did it. To push against boundaries for no reason other than that they exist. That's not inherently wrong, but it might not justify the costs. Because the costs aren't just material, they're human. Generations would be born and die in transit, their entire lives spent traveling toward a destination they'll never see. What do you tell them? That their existence serves a purpose they'll never experience? That their lives are means to an end that won't materialize for thousands of generations? How do you maintain morale, purpose, meaning when the goal is so distant that it's effectively infinite? The journey to escape the Milky Way reveals something profound about our place in the universe. We're not meant to leave. Not in the sense that some cosmic force prevents it, but in the practical sense that the universe's structure makes it extraordinarily difficult, perhaps impossible, for biological beings to traverse intergalactic distances. The scales are wrong, the energies are wrong, the timescales are wrong. Everything about the cosmos seems calibrated to keep galaxies isolated from each other, separate islands in an expanding ocean of space-time that grows larger and more uncrossable with every passing moment. If biological life can't survive the journey, perhaps intelligence itself needs to change form. Digital consciousness uploaded to machines that don't age, don't require food or water, don't suffer bone loss or muscle atrophy. Artificial intelligence that can wait centuries between thoughts if necessary, slowing its processing speed to conserve energy during the long dark between stars. This isn't science fiction anymore. We're already creating AI systems that exceed human capability in narrow domains. The question isn't whether machine intelligence is possible. We're watching it emerge. The question is whether consciousness, The subjective experience of being can transfer from biological neurons to silicon substrates. Nobody knows. We don't even understand consciousness well enough to know if it's transferable. Maybe it's an emergent property of biological neural networks that can't exist in other mediums. Maybe it's substrate independent and could run on anything sufficiently complex. The philosophical debates are endless and unresolved, but assume it works. Assume you could upload your mind, your memories, your sense of self into a machine designed for interstellar travel. You'd still face the same fundamental problems: energy, time, distance. The machine body needs power. Solar panels work near stars, but become useless in the void between galaxies, where starlight is too dim to harvest. Nuclear reactors run on fuel that eventually depletes. Fusion requires hydrogen you'd have to collect from space, and intergalactic space is even emptier than interstellar space. You're back to the same constraints, different package, same physics. What about sending information instead? Not physical spacecraft, but radio signals carrying the blueprint for reconstructing human consciousness. Broadcast your mind into space and let something on the other end rebuild you from the pattern. This solves the propulsion problem. Electromagnetic waves travel at light speed without requiring fuel. You could reach Andromeda in 2.5 million years, still astronomical by human standards, but theoretically achievable. The challenges multiply immediately. You need a receiver on the other end. Some civilization or automated system capable of detecting your signal, decoding it, and reconstructing whatever information it contains. You're broadcasting blindly into the void, hoping someone's listening. Even if they are, even if some alien civilization picks up your transmission and reconstructs your consciousness, what have you actually accomplished? You're now a digital ghost in an alien computer, assuming they even run the program. Maybe they just study the data structure without executing it. Maybe their technology is incompatible and the information is meaningless to them. And you, the original you, are still here. You didn't escape anything. You created a copy that might or might not be experiencing existence somewhere else, while you continue living and dying in the Milky Way. This gets into deep questions about identity and continuity of consciousness. If you copy your mind perfectly, is the copy you? If the original dies, does it matter that the copy survives? Philosophers have debated this for decades with no consensus. The practical reality is worse. The bandwidth required to transmit a human consciousness, every neural connection, every memory, every detail that makes you who you are, would be staggering. We're talking about petabytes or exabytes of information, and that's assuming we could even map a brain that completely. Transmitting that much data across millions of light years would take centuries at minimum. The signal would degrade. Cosmic radiation would corrupt bits. By the time it arrived, if it arrived, it might be too damaged to reconstruct anything coherent. You'd need error correction so robust that the message could survive 1 million years of interference. That means redundancy, sending the same information multiple times in multiple ways, which multiplies the already impossible bandwidth requirements. Some proposals suggest sending simpler information, not complete consciousness, but instructions for building it, like DNA for minds. Send the code for human intelligence and let the receivers run their own simulations based on those rules. This reduces data requirements but sacrifices fidelity. What emerges on the other end would be human-like, but not you specifically. It would be a reconstruction based on general principles, rather than your particular memories and personality. Is that enough? Is generic human intelligence surviving somewhere in the universe sufficient? Or does it need to be this specific instance of consciousness, experiencing continuity from your current moment? There's no objective answer. It depends what you value, what you consider survival, what matters to you about existence itself. But zoom out from individual consciousness entirely. Maybe the goal isn't preserving any specific mind, but ensuring something from Earth persists beyond our galaxy. Information about who we were, what we discovered, what we created. The Voyager Golden Record already does this on a tiny scale. A phonograph record attached to Voyager 1 containing sounds and images from Earth, instructions for playing it, greetings in multiple languages, a message in a bottle thrown into the cosmic ocean. Voyager will drift through interstellar space for millions of years, potentially outlasting human civilization, potentially being found by someone or something that can decode it. It's already our emissary beyond the solar system, though it will never leave the galaxy. You could scale this up. Send thousands of probes in all directions, each carrying comprehensive information about Earth, human civilization, our scientific knowledge, our art and music and literature. Digital time capsules designed to survive cosmic radiation and drift indefinitely through space. Some would be destroyed by collisions with debris. Some would fail mechanically. But scatter enough of them, and probability suggests at least one survives long enough to be found by something capable of understanding it. This is closer to achievable than crewed missions. You don't need life support or artificial gravity or solutions to biological problems. Just robust data storage and error correction, radiation shielding for the electronics, and enough power to transmit periodically in case someone's listening. The cost is everything human. No consciousness experiences the journey. No one arrives anywhere. Just information, preserved and broadcast, waiting for receivers that might never exist. Is that enough? Does it count as escaping if nothing alive makes the trip? Maybe it has to be. Maybe that's the only escape available within the boundaries physics imposes. Not bodies crossing the void, but information propagating outward, patterns persisting even after their original substrate decays. The universe might not permit matter to travel between galaxies, but it does allow information to propagate. Light from distant galaxies reaches us despite the vast distances involved. The cosmic microwave background carries information from 380,000 years after the Big Bang, encoded in temperature fluctuations we can still measure today. Information persists. Matter decays. Maybe that's the answer. But accepting that answer means abandoning the dream of exploration, of humans experiencing other galaxies firsthand, of consciousness expanding beyond the Milky Way's boundaries. It means accepting that we're trapped here not as individuals, or even as a species, but as a category of being, biological life bound by metabolic requirements and generational timescales. Unless something changes, unless our understanding of physics is incomplete. We've been wrong before. Newton's gravity seemed complete until Einstein revealed its limitations. Classical physics seemed comprehensive until quantum mechanics emerged. Every time we've thought we understood the fundamental rules, deeper investigation revealed new layers. Maybe faster than light travel exists in some form we haven't discovered. Maybe wormholes are possible. Maybe higher dimensions provide shortcuts through space-time. Maybe quantum entanglement has applications we haven't conceived. The mathematics doesn't currently support any of this. General relativity prohibits faster-than-light travel without exotic matter that probably doesn't exist. Wormholes require negative energy densities we've never observed. Higher dimensions remain theoretical constructs without experimental evidence. But absence of evidence isn't evidence of absence. We've only been doing physics seriously for a few centuries. We've only been looking at the universe with modern instruments for decades. Drawing final conclusions about what's possible seems premature. That said, hope isn't a strategy. Banking on future physics discoveries to solve current impossibilities is wishful thinking, not planning. The responsible position is acknowledging that escaping the Milky Way appears impossible, given everything we currently know, while remaining open to the possibility that we don't know everything. Which brings us back to the fundamental question: should we even try? Resources are finite. Time is limited. Energy spent attempting to escape the galaxy is energy not spent on problems closer to home. We haven't colonized our own solar system yet. We haven't established self-sustaining habitats beyond Earth. We haven't solved the technical challenges of traveling to Mars reliably, let alone other star systems. Maybe the focus should be there first. Master interplanetary travel. Establish permanent bases throughout the solar system. Then attempt interstellar journeys within the Milky Way. Work outward in achievable steps rather than leaping toward impossible goals. The galaxy contains hundreds of billions of stars. Even if only a tiny fraction have habitable planets, that's still millions of potential homes for humanity. Reaching those would take centuries or millennia with realistic technology, but it's achievable in principle. The distances are vast, but not impossible. Escaping the galaxy entirely serves no practical purpose beyond symbolism. It doesn't make humanity safer, quite the opposite given the dangers involved. It doesn't provide access to resources we couldn't find within the Milky Way. It doesn't solve any problem that needs solving. The only reason to attempt it is philosophical. Because it's there. Because we can. Because pushing boundaries is what humans do. That's not nothing. Exploration for its own sake has driven human achievement throughout history. We climbed Everest because it was the highest mountain. We went to the moon because it seemed impossible. We probe the nature of reality because we're curious. Maybe attempting to escape the galaxy, even knowing it's probably impossible, serves a purpose beyond the practical goal. Maybe the technologies developed while trying would have applications elsewhere. Maybe the attempt itself teaches us things worth knowing. Or maybe it's hubris. Maybe recognizing our limitations is wiser than raging against them. The universe is vast beyond human comprehension. The Milky Way alone contains more stars than we could visit in 1,000,000 lifetimes. The local galactic neighborhood contains thousands of galaxies within relatively short distances, cosmologically speaking. We're already part of something magnificent. Maybe escaping it isn't the goal. Maybe understanding it is enough. The psychological dimension deserves its own examination because it might be the most insurmountable barrier of all. Consider what happens to the human mind during isolation. Antarctic research stations provide our closest analog. 6 months in winter darkness with the same small group. No escape possible. No way home until spring. Psychological screening is rigorous. Support systems are extensive. And still people crack. Now multiply that isolation by factors of thousands. Not months, but decades. Not a small base, but a sealed metal tube hurtling through absolute void. not temporary separation, but permanent exile from everything humans have ever known. You'd never see Earth again, never breathe unfiltered air, never feel rain, never walk on solid ground that isn't artificial. The stars outside your window wouldn't change position perceptibly across your entire lifetime. The universe would appear frozen, static, dead. Communication with home would become increasingly difficult as distances grew. Speed of light limitations mean conversations turn into correspondence. A message home taking years to arrive. The response taking years to return. By the time you hear back from Earth, the people you knew might be gone. What does that do to someone? What happens when you realize everyone you've ever known is aging and dying while you float through emptiness? When you understand that returning is physically impossible, that you've traded everything familiar for eternal exile, Antarctic crews can look forward to going home. Space station astronauts know their tour ends. Even Mars colonists could theoretically return. Escaping the galaxy offers no such comfort. It's one way, forever. The psychological research on long-duration spaceflight is limited but concerning. 6-month ISS missions produce measurable cognitive changes. Attention spans decrease. Reaction times slow. Spatial reasoning deteriorates. These effects reverse after returning to Earth. What happens when there's no return? When the mission spans not months, but lifetimes? Do the effects compound? Does the brain adapt, or does function continue degrading? We don't know. Nobody's tried it. The longest any human has spent continuously in space is 437 days. Valery Polyakov aboard Mir. He returned with physical and psychological effects that took months to resolve. And he knew he was coming home. Now imagine generations born in space. Children who've never experienced planetary gravity. Adults who've never seen a horizon, never encountered weather, never known anything beyond metal corridors and recycled air. What does that do to human psychology, to culture, to our fundamental sense of what it means to be human? Some researchers argue we'd adapt. Humans are extraordinarily flexible. We've colonized every environment on Earth, from Arctic tundra to tropical jungles. We've created thriving cultures in the most hostile climates. Why not space? But every Earth environment, no matter how extreme, provides certain constants. Gravity, day-night cycles, the presence of a biosphere, however sparse, access to Earth's magnetic field protecting from radiation. These aren't just conveniences, they're the environmental parameters within which human biology evolved. Remove them completely, and you're conducting an experiment that's never been tried. The results are unpredictable. Social dynamics present another concern. Small, isolated groups develop complex dynamics. Personality conflicts that would be minor annoyances in normal life become major problems when there's no escape. Hierarchies form. Factions emerge. Tensions build. On Earth, unhappy people leave. They find new jobs, new cities, new social groups. In a spacecraft hurtling through intergalactic space, there's nowhere to go. You're stuck with the same people forever. You and your children and your children's children, all sealed together in a metal tube for generations. Historical isolated expeditions often ended badly. Arctic explorations descended into madness and cannibalism. Long sea voyages produced mutinies. Religious communities sealed themselves away and imploded in violence. These were temporary situations with the possibility of escape or rescue. A galactic escape mission offers neither. You'd need to create a stable society capable of maintaining itself across potentially thousands of generations. Every social structure we've ever built has eventually collapsed or transformed beyond recognition. Governments fall, religions split, cultures evolve into something unrecognizable within centuries. Can you design a social system that remains stable for 10,000 years? For 100,000? While sealed in a spacecraft with zero external input and no possibility of escape? The mission architecture itself creates problems. Someone has to maintain the ship. Someone has to grow food. Someone has to manage life support. These aren't optional tasks, they're survival requirements. Failure means death for everyone. In normal societies, people choose occupations based on interest and aptitude. Some flexibility exists. If you hate your job, you can change careers. In a spacecraft, certain functions must be filled regardless of preference. The life support specialist who wants to be an artist doesn't have that option. The ship needs life support maintained. How do you create a society that can compel necessary work without becoming tyrannical? How do you maintain motivation across generations of people who had no choice in their mission, who were born into a situation they never agreed to? The children are the real ethical nightmare. The first generation chose their fate. They knew what they were signing up for. Every subsequent generation is born without consent into permanent imprisonment. They'll grow up hearing stories about Earth, a planet they'll never see. They'll learn about forests and oceans and open sky, none of which they'll ever experience. They'll be told they're part of a great mission. But what does that mean to someone who had no choice? How do you prevent resentment? How do you maintain purpose across generations when the goal, escaping the galaxy, is so distant and abstract that it's essentially meaningless to anyone who'll actually achieve it? Some argue you don't tell them. You create a closed culture where Earth becomes myth, where the ship is the only reality anyone knows, where the mission continues because it's simply what you do, like breathing. But that requires deliberate cultural engineering, controlled information, managed history. It requires creating and maintaining lies across generations. Is that ethical? Is it even possible? Information wants to spread. Secrets leak. People question. Eventually, someone discovers the truth, that they're in a metal tube hurtling through void, that their entire existence is artificial, that they've been lied to their whole lives. What happens then? Does the society survive that revelation? Or does it collapse into nihilism and despair? The genetic dimension adds another layer of horror. Small populations accumulate genetic problems. Inbreeding increases. Even with careful planning and genetic diversity management, a ship population of thousands faces inevitable genetic degradation over generations. You'd need active genetic management, controlled reproduction, possibly genetic engineering to maintain diversity and health. That means someone making decisions about who reproduces with whom. Someone deciding which genetic lines continue and which end. In normal societies, that's called eugenics. It's considered one of history's great moral horrors. But in a closed ship population, it might be necessary for survival. The alternative is genetic collapse leading to extinction. How do you implement necessary eugenics without creating a dystopian nightmare? How do you give people reproductive freedom while ensuring genetic health of the population? These aren't abstract philosophical questions. They're practical problems that would need solving. Then there's the knowledge problem. Maintaining technical knowledge across generations becomes crucial. The ship needs constant maintenance. Systems need repair. Technology needs operation by people who understand it. In normal civilization, knowledge is distributed. Specialists exist in every field. If one person dies, others can fill their role. Universities train new experts. Information is redundant across millions of people. On a ship, you have thousands at most, possibly hundreds. Losing key technical knowledge could be catastrophic. If the fusion engineer dies before adequately training a replacement, the ship might lose power. If the genetic database becomes corrupted and nobody knows how to fix it, the population faces genetic collapse. You'd need robust education systems maintained across generations, technical knowledge preserved and transmitted reliably. But education requires resources, time, energy, materials. It requires people willing to learn and teach. It requires society valuing knowledge preservation above short-term convenience. Can you guarantee that across 1,000 generations? Human history suggests not. The Library of Alexandria burned. Medieval Europe forgot Roman engineering. The Dark Ages saw massive knowledge loss. These were civilizations of millions with external contact and new knowledge flowing in. A ship is isolated, closed, dependent entirely on preserving what it starts with. One forgotten maintenance procedure could doom everyone. One lost piece of technical knowledge could make critical repairs impossible. The margin for error is zero, and lurking beneath everything is the question of purpose. Why are we doing this? The first generation knows: escape the galaxy, explore the universe, ensure human survival. Noble goals that justify sacrifice. But what about Generation 50? What about Generation 500? The goal remains distant, abstract, essentially unreachable within any individual lifetime. The mission that started as exploration becomes simply existence. The ship that was a means to an end becomes the end itself. How do you maintain purpose when the purpose is so divorced from daily life that it becomes meaningless? How do you prevent society from forgetting why the journey started and simply existing out of habit? Some argue purpose would emerge naturally. Humans create meaning. We find goals and build cultures even in the most constrained circumstances. A ship society would develop its own purposes, its own reasons for continuing, independent of the original mission. Maybe that's enough. Maybe a thriving society that's forgotten its original purpose is acceptable. As long as people are happy and the ship continues, does it matter if they remember Earth or care about escaping the galaxy? But that assumes society remains stable and thriving. It assumes no catastrophic failures, no social collapse, no descent into violence or despair. It assumes humans can maintain function in an environment utterly alien to everything our species evolved for. That's an enormous assumption, one we have essentially no evidence supporting. The terrifying truth is that the psychological and social challenges of escaping the Milky Way might be completely unsolvable. Not because we lack technology or resources, but because humans simply aren't built for it. Our brains evolved for life on Earth. Our social structures developed in planetary contexts. Our psychology depends on environmental inputs that don't exist in deep space. You can't engineer your way around fundamental human nature. You can't design a social system that overrides millions of years of evolution. You can't create artificial meaning that replaces the deep purposes that emerge from living on a living world. Maybe that's the real barrier. Not physics or engineering, but the simple fact that humans need Earth. Not just as a place to live, but as the context that makes human existence meaningful. Strip away the planet, the biosphere, the connection to evolutionary history, and what remains might not be recognizably human anymore. It might not be anything worth preserving. Hyphenated scenarios pose questions we can't answer because we've never faced them. And perhaps that's the most terrifying aspect of all. Not knowing whether survival is possible doesn't mean stopping the attempt. History rewards those who try impossible things. Sometimes they succeed. Sometimes they create something unexpected. Sometimes they simply prove what's achievable and what isn't. All outcomes have value. So what does attempting galactic escape actually look like? Not in science fiction where problems solve themselves conveniently. In reality where physics imposes hard limits and engineering faces constraints that don't disappear through narrative convenience. Start with propulsion. Chemical rockets won't work. We've established that thoroughly. The energy density is insufficient, and the mass ratios become absurd at the scales required. You'd need a rocket larger than Earth to carry enough fuel for meaningful fractions of light speed. That's not engineering limitation. That's fundamental physics saying no. Nuclear propulsion offers improvements. Fission provides higher energy density than chemical reactions. Fusion would be better still. The same process powering stars, releasing enormous energy from hydrogen fuel. But fusion propulsion remains theoretical. We haven't achieved sustained fusion on Earth yet, let alone built engines capable of propelling spacecraft. The engineering challenges are staggering, containing plasma at millions of degrees, directing thrust efficiently, achieving power outputs that make the journey remotely feasible. Even with fusion, the numbers are daunting. To reach 10% light speed, slow by galactic escape standards, requires energy equivalent to the total power output of human civilization for extended periods. And that's just for a small probe. Scale up to generation ships carrying thousands of people with all necessary infrastructure. The energy requirements become astronomical. Antimatter represents the theoretical maximum. When matter and antimatter meet, they annihilate completely, converting mass to energy with perfect efficiency, according to E equals mc squared. Nothing provides higher energy density. But antimatter doesn't exist naturally in quantities we can use. We'd have to manufacture it, particle by particle, using particle accelerators. Current production rates, a few nanograms per year. A single gram would require more energy than humanity produces annually. The quantities needed for spacecraft propulsion are millions of times larger. You could imagine future breakthroughs making antimatter production efficient. But you're still carrying fuel that explodes if containment fails even briefly. One malfunction, and the ship becomes the largest explosion in local space. The safety challenges alone might prove insurmountable. Beamed propulsion offers an alternative. Instead of carrying fuel, the ship receives energy from external sources. Giant lasers based in solar orbit beam power to the spacecraft, pushing it via light sail or heating propellant for thrust. This solves the mass ratio problem. The ship doesn't carry fuel, so it can be lighter and achieve higher velocities. But beamed propulsion creates new problems. The beam must remain focused across astronomical distances. Even slight divergence means the energy misses the ship entirely. You'd need targeting precision beyond anything currently achievable. maintained for decades or centuries as the ship accelerates. And the power stations themselves would be megastructures requiring resources and engineering capabilities we don't possess. Then there's deceleration. Accelerating is only half the journey. If you want to stop at a destination, rather than flying past at relativistic velocity, you need equal energy for slowing down. Beamed propulsion can't help. You're too far from the beam source. You'd need onboard fuel for deceleration, bringing back all the mass ratio problems you tried to avoid, unless you don't plan to stop. A ship accelerating continuously, never decelerating, escaping the galaxy and continuing into intergalactic space indefinitely. But what's the point? You can't explore if you're moving too fast to interact with anything. You can't colonize if you can't stop. The mission becomes purely existential, survival for its own sake with no external purpose. Some propose generation ships traveling at modest velocities, not relativistic speeds requiring exotic propulsion, but achievable velocities using advanced versions of current technology. 10% light speed might be reachable with nuclear pulse propulsion, detonating atomic bombs behind the ship and riding the shockwave. Crude, but theoretically functional. At 10% light speed, crossing the galaxy takes 1,000,000 years. Escaping the galactic gravitational well entirely might take several million. Those timescales make generation ship challenges unavoidable. You're not talking about a few generations weathering the journey. You're talking about thousands of generations living and dying aboard the ship, so many that the original mission becomes mythology, then is forgotten entirely. Could you design social systems stable over such timescales? Human civilizations on Earth rarely last more than a few centuries before fundamental transformation. Governments rise and fall. Cultures evolve beyond recognition. Languages diverge until mutual comprehension fails. And that's with planetary resources, external contact, and environmental variety. A ship is closed, isolated, unchanging in its fundamental environment. The social dynamics would be unlike anything in human history. Closest analogy might be extremely isolated communities, remote islands, mountain valleys cut off from outside contact. Those communities often develop unusual social structures, sometimes stable, sometimes dystopian. But even they have more environmental variety than a spacecraft. You'd need governance systems that maintain function across millennia, legal frameworks that adapt to changing circumstances without losing core stability, educational systems that preserve essential knowledge while allowing cultural evolution, economic systems that manage finite resources without creating destructive inequality. All of this in an environment where failure means extinction. No rescue is possible, no escape available. The psychological burden would be crushing. Every generation knows they're born into a prison they can never leave, living lives entirely in service to a mission they'll never see completed. Some might find meaning in that. Many wouldn't. How do you prevent despair from becoming endemic? How do you maintain mental health when the environment is fundamentally unnatural for human psychology? You could argue that the environment would become normal for people born into it. They'd know nothing else. The ship would be their world, as natural to them as Earth is to us. But humans aren't infinitely adaptable. We have biological needs, psychological requirements, social instincts that developed over millions of years of planetary existence. You can't engineer those away or expect them to disappear through cultural adjustment. Maybe the answer is abandoning biological humans entirely. Send artificial intelligence instead. Minds that don't need life support, don't experience psychological distress from isolation, don't require multi-generational social structures. AI could potentially survive journeys of any length, maintaining purpose and function indefinitely. But that changes the mission fundamentally. You're not escaping the galaxy. You're sending ambassadors, representatives, echoes of humanity, rather than humans themselves. Is that acceptable? Does it achieve the goal of preserving human existence? Or is it just launching our legacy into the void while we remain bound to our planetary cradle? Some find that distinction meaningless. Intelligence is intelligence. Consciousness is consciousness, regardless of substrate. If AI carries human knowledge, values, culture, then human civilization continues, even if biological humans don't. Others see it as fundamental betrayal, giving up on actual human survival and settling for digital ghosts. There's no objective answer. It's philosophy, not physics. But it matters because it determines what we're actually trying to accomplish. Preserve biological humans specifically. Then generation ships with all their challenges are necessary. Preserve human knowledge and culture. AI might suffice. Ensure intelligence originating from Earth continues existing somewhere in the universe. That's an entirely different goal with different solutions. Each framing changes what counts as success and what represents acceptable sacrifice. Meanwhile, physics continues imposing constraints that don't care about our philosophical positions. Relativity limits maximum velocity. Thermodynamics requires energy expenditure for any action. Biology demands specific conditions for human survival. These aren't negotiable. They're features of reality we must work within. Maybe the answer is accepting that escaping the galaxy isn't achievable for biological humans using any foreseeable technology. Not because we lack imagination or determination, but because the universe simply doesn't permit it. The distances are too vast, the timescales too long, the energy requirements too extreme, the biological constraints too fundamental. That's not defeatism. It's honest assessment of limits. Some things are impossible, not because we haven't tried hard enough, but because reality works a certain way. You can't travel faster than light regardless of technological advancement. You can't violate conservation of energy, no matter how clever your engineering. Maybe you also can't maintain human civilization for millions of years in deep space isolation. Accepting limits doesn't mean abandoning all exploration. The solar system remains available. Interstellar travel to nearby stars might be achievable, even if galactic escape isn't. We could become a multi-star species without ever leaving the galaxy. That's still extraordinary expansion compared to our current single-planet existence. Or maybe we're asking the wrong question entirely. Why escape the galaxy? What actual benefit does it provide beyond the abstract satisfaction of having done something difficult? The galaxy contains hundreds of billions of stars. Even if only a tiny fraction have habitable planets, that's still millions of potential worlds. We could expand throughout the galaxy for millions of years before approaching any resource limits. Galactic escape becomes relevant only on timescales where the galaxy itself becomes uninhabitable, when star formation ceases and existing stars begin dying, billions of years in the future. By that point, humanity will either have evolved into something unrecognizable or gone extinct from other causes. Worrying about galactic escape is like cavemen worrying about smartphone battery life. The concerns are so disconnected from present reality that planning for them is essentially meaningless. Yet the question persists. Something about it captures imagination in ways that practical concerns don't. Maybe because it represents the ultimate frontier, the final boundary. We've explored Earth. We're beginning to explore the solar system. We imagine interstellar travel. Galactic escape is the limit case, the furthest possible extension of human reach. Or maybe it's simpler. Maybe we ask because we can ask. Because humans are the kind of species that wonders about impossible things. Because the ability to conceive of galactic escape, even if we can never achieve it, is itself remarkable. The universe doesn't care whether we escape the galaxy. It doesn't care whether we survive at all. The Milky Way will continue spinning. Stars will continue forming and dying. The cosmos will evolve according to physical law, completely indifferent to human existence. But we care. We wonder. We imagine. We calculate what it would take and discover the answer is more than we can give. That discovery matters not because it changes anything cosmic, but because it reveals something about us, our capabilities, our limits, and the strange, persistent drive to push against boundaries, even when we know they won't move. The journey to escape the Milky Way remains terrifying, not because we might attempt it and fail, but because we probably won't attempt it at all. We'll realize the costs exceed any possible benefit, the challenges surpass our capabilities, the timescales exceed our relevance. We'll make peace with being a galactic species at most, if we're lucky. Probably just a multi-star species, possibly forever limited to our solar system. That's the real terror. Not the journey itself, but confronting the limits of what's achievable and discovering we're smaller than we hoped. Not in importance, that's subjective anyway, but in reach, in the scale of what we can actually accomplish versus what we can imagine. The universe is vast beyond comprehension. The galaxy alone contains more stars than humans who have ever lived. And we're confined to the tiniest fraction of it, not by choice, but by physics, by biology, by the fundamental architecture of reality that doesn't bend to accommodate our ambitions. We're trapped not in a prison, but in a context. The galaxy isn't keeping us here through malice. It's simply too large, too energetic, too fundamentally different from our scale of existence for escape to be meaningful. We're planetary creatures contemplating cosmic journeys, using tools barely sufficient for interplanetary travel. The gap between what we want and what's possible isn't closing. If anything, the more we learn about the universe, the more clearly we see how constrained we actually are. Each new discovery reveals additional complications we hadn't considered, additional barriers we didn't know existed. That's not cause for despair. It's cause for perspective, for appreciating what we have rather than mourning what we can't achieve, for finding meaning in the scope of existence available to us rather than lamenting the larger scope that isn't. The Milky Way isn't a prison. It's a home containing more worlds than we could explore in millions of years, more possibilities than we could exhaust in any time frame relevant to human civilization, more than enough space for everything we might actually want to accomplish. Escaping it was never the point. Understanding why we can't, that's where the real insight lives. The Milky Way isn't holding you prisoner. That's not what's happening here. You're caught in something more fundamental than captivity. You're part of a system operating at scales where human intentions become irrelevant, where physics writes rules that don't care about determination or ingenuity, or the persistent human belief that wanting something badly enough makes it achievable. The galaxy's gravitational embrace isn't malicious. It's geometry. Mass curves space-time. Objects follow geodesics through that curvature. You're not being held. You're simply existing within the natural structure of reality at cosmic scales. Escaping requires overwhelming that structure with energy and velocity beyond anything biological life can reasonably achieve or survive. Every barrier examined throughout this journey, propulsion, radiation, distance, time, psychology, social stability, represents not temporary limitation awaiting technological breakthrough, but fundamental constraint imposed by how the universe actually works. The speed of light isn't a challenge to overcome through clever engineering. It's the maximum rate at which causality propagates through space-time. The inverse square law diminishing beam intensity over distance isn't poor design requiring correction. It's mathematical consequence of three-dimensional space. You could imagine futures where these constraints matter less. Civilizations spanning millions of years developing technologies we can't conceive. Intelligence transcending biological substrates entirely, becoming something that doesn't require planetary environments or generational continuity. Minds that could wait centuries between thoughts, slowing their processing to conserve energy during million-year journeys through absolute void. But those aren't humans anymore, not in any meaningful sense. Their descendants so transformed that the connection to Earth-born biology becomes theoretical rather than actual. At that point, you're not preserving human civilization. You're watching it evolve into something alien that happens to carry our legacy in its source code. Maybe that's acceptable. Maybe intelligence continuing in any form justifies abandoning the specific configuration that started the chain. Or maybe preserving biological humanity matters in ways that can't be reduced to information patterns and cultural inheritance. The question has no objective answer because it's ultimately about values, not facts. What remains factual is this: humans, as we currently exist, cannot escape the Milky Way. Not won't, can't. The energy requirements exceed our capacity to generate or store. The timescales exceed our biological and social sustainability. The environmental challenges exceed our physiological tolerances. The isolation exceeds our psychological resilience. Each individual barrier might theoretically yield to sufficient advancement, but they don't exist separately. They compound. Solving propulsion makes radiation worse. Solving radiation adds mass. Adding mass makes propulsion harder. Extending journey time multiplies psychological and social challenges. Every solution creates new problems that recreate the original impossibility in different form. This isn't temporary technological limitation. It's reality operating at scales fundamentally mismatched to human existence. The universe didn't design itself around making biological intelligence comfortable. It doesn't care whether we explore or stagnate or go extinct. The physical laws that make galaxies possible also make them nearly impossible to leave. That's not cruelty. That's just how geometry and thermodynamics work when applied to structures containing hundreds of billions of stars. Accepting this doesn't mean surrendering curiosity or abandoning exploration. The galaxy remains vast beyond human comprehension. Hundreds of billions of stars, trillions of planets, more worlds than we could visit in millions of years, even with perfect interstellar travel. The scope available within our gravitational prison exceeds anything previous generations imagined possible. Earth's surface seemed infinite to early humans. Then we mapped it, crossed oceans, circumnavigated the globe. The solar system became our expanded horizon, planets and moons offering destinations for centuries of exploration. Beyond that lie the stars, thousands of them potentially reachable within timeframes that stretch but don't break human civilization's continuity. That's extraordinary. That's more than enough. The fact that galactic escape remains beyond reach doesn't diminish what's achievable within the boundaries physics actually permits. The terror of escaping the Milky Way comes not from the journey's difficulty, but from confronting what it reveals about human significance. We're products of one planet, orbiting one star, in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The scales are so disproportionate that our entire existence becomes cosmically negligible, except it's not. Significance isn't measured by spatial volume or temporal duration. It's measured by complexity, by experience, by the emergence of consciousness from matter. A single human mind contains more functional complexity than most stellar systems. The ability to contemplate galactic escape, even recognizing its impossibility, demonstrates something remarkable about what matter can become when organized correctly. You're not trapped in the Milky Way, you're part of it. Your atoms were forged in stellar cores. Your existence depends on galactic processes operating over billions of years. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created through nuclear fusion in massive stars that exploded long before Earth formed. You're not separate from the galaxy trying to escape. You're the galaxy becoming conscious of itself, temporarily, locally. In this specific configuration of matter and energy that happens to be reading these words right now, that configuration will end. You'll die. Humanity will likely go extinct eventually. The sun will exhaust its fuel. Earth will become uninhabitable. Given enough time, every star in the galaxy will burn out, and the Milky Way itself will become a graveyard of stellar remnants, slowly radiating their heat into the expanding void. None of that matters to the present moment. Right now, you exist. You're aware. You can contemplate impossibilities and calculate their exact degree of impossibility. You can understand why the universe works the way it does, even when that understanding reveals your own cosmic insignificance. The Milky Way contains you not as prisoner, but as participant. The same physical laws that make escape impossible also make your existence possible. Gravity that traps you in the galactic potential also allowed stars to form, planets to coalesce, life to emerge. The speed of light that limits maximum velocity also ensures causality remains coherent and reality stays logically consistent. You can rage against these constraints or accept them. Either way, they remain unchanged. Physics doesn't negotiate. The universe doesn't compromise. What's impossible stays impossible, regardless of how badly you want it or how hard you try. But impossibility of one thing doesn't preclude possibility of others. You can't escape the galaxy. You can explore the solar system. You can potentially reach nearby stars. You can understand the cosmos with increasing precision, even when that understanding reveals limits to what you'll ever experience directly. Maybe that's enough. Maybe understanding is its own form of transcendence, not physical escape from constraints, but intellectual grasp of why those constraints exist and what they mean. You'll never leave the Milky Way, but you can know exactly why. You can calculate the energy required, map the distances involved, understand the physics preventing it. That knowledge doesn't change the impossibility, but it transforms your relationship to it. You're not helplessly trapped, you're consciously bounded. There's dignity in that distinction, in recognizing limits while refusing to let those limits diminish curiosity or wonder or the drive to explore within the scope actually available. The journey to escape the Milky Way is terrifying because it's impossible. Not movie impossible, where the hero overcomes through determination and cleverness. Actually impossible. The way traveling faster than light is impossible. The way violating conservation of energy is impossible. The universe has rules. Some of them don't bend. Living within those rules while understanding them completely, that's the real human achievement. Not escaping the galaxy, but comprehending why escape remains beyond reach. Not transcending physical law, but grasping its structure with sufficient precision to calculate exactly what it permits and prohibits. You're trapped in the Milky Way. So is everyone else. So is everything that emerged from Earth's biosphere. The atoms that compose your body will remain gravitationally bound to this galaxy long after they've stopped being you. They'll cycle through other forms, dispersed in interstellar space, incorporated into new stars, scattered by supernovae. But they won't leave. The galaxy's grip extends beyond your lifetime, beyond human civilization's lifetime, beyond timescales where the distinction between past and future retains meaning. That's not tragedy, that's context. The framework within which everything you'll ever do or experience or understand takes place. Fighting against it accomplishes nothing because there's nothing to fight, just geometry and thermodynamics operating at cosmic scale, indifferent to human ambitions. The Milky Way will continue spinning long after you're gone. Stars will form and die. The supermassive black hole at the galactic center will consume matter and emit radiation. The spiral arms will rotate. Everything will proceed according to physical law, exactly as it always has, completely unconcerned with whether any particular configuration of matter achieved its goals or died trying. Your escape was never possible. The terror comes from facing that directly, from calculating the exact energy required and realizing it exceeds what's achievable, from mapping the distances and understanding they're too vast, from examining the timescales and recognizing they're too long, from considering the psychological toll and admitting it's too crushing. The universe is vast. You are small. The galaxy is ancient. You are temporary. Those facts don't change regardless of technological advancement or cultural evolution or desperate determination to overcome them. What does change is your relationship to those facts. You can deny them, ignore them, pretend they don't matter, or you can face them completely, understand them precisely, and find meaning within the boundaries they impose rather than despite them. The Milky Way isn't your prison, it's your home, the only one you'll ever have, the only one anything descended from Earth will ever have. That's not limitation requiring mourning, that's reality requiring acceptance. And in that acceptance, maybe something shifts. Not the physics, those remain immutable, but the perspective. The recognition that being bound to one galaxy among hundreds of billions doesn't diminish the scope of possible exploration and discovery and understanding available within that constraint. You can't escape. Nobody can. Nothing can. The Milky Way holds you not through walls or barriers, but through the fundamental architecture of space-time itself, And that's fine. That's exactly as it should be, because you were never meant to leave. You were meant to be here now, part of this ongoing cosmic process that began billions of years ago and will continue billions of years into the future. Your role in that process is microscopic, temporary, ultimately insignificant measured against galactic timescales. But significance isn't measured that way. It's measured by the fact that you can have this realization at all. That matter organized itself into a configuration capable of understanding its own cosmic context and recognizing its limitations, while refusing to let those limitations destroy wonder. The journey to escape the Milky Way ends where it began. Here, in gravitational embrace that can't be broken, with better understanding of why that's true and what it means. The terror fades, not because the impossibility changes, but because impossibility stops feeling like failure once you truly comprehend it. You're not escaping. You never were. And somehow, understanding that completely makes being trapped feel less like confinement and more like belonging to something vast enough that escape becomes meaningless anyway.